Hello, it's time for some maths, or should I say, it's velocity time for some maths, because we're looking at velocity time graphs today, and we're going to be looking at drawing them and using them to help us solve some problems. What I should start off by looking at is explaining what the word velocity actually means, because some of you might not know what it means. And velocity means, basically, well, speed. It tells us how fast something's travelling, but it tells us more than speed. That's why we've got a different name for it. It not only tells us the speed, but it also tells us the direction an object is travelling in. It can do that in more than one way, but one of the most simple ways velocity can tell you the direction something's travelling in is if you're in just 1D or one dimension. It just uses a plus or a minus in front of the number to tell you if you're effectively going forwards or backwards, which is linked to the whole idea of positive direction, which is something I mentioned in my How to Approach Mechanics video, which acted as an introduction to this stuff. So go and have a look at that video if you don't know what I'm talking about and you haven't seen that video yet. But to continue on that note, an example of that would be me, for instance, saying, okay, let's say on this page, going to the right is my positive direction. Therefore, if I had an object and let's say it was traveling at 3 meters per second to the right, then we would label that as having a velocity of positive 3 because the direction it's traveling in is the positive direction. Whereas if we had that same object and it was still traveling 3 meters per second, but it was traveling 3 meters per second to the left, then that would be a velocity of minus 3 because it's going in the negative direction. And then one more thing I'd like to point out is that at rest is a term that you need to watch out for in questions mentioning velocity, because at rest means velocity equals 0. So, with all that said, let's start by going through an example, because although I could talk more about explaining what a velocity time graph is, it's actually easier to just do that by doing an example. So here is our example, and the beginning bit is mentioning that we've got a cyclist moving along a straight road, and that's not really telling us that much information, except the fact it's telling us it's along a straight road means we're effectively dealing with a 1D situation, because we're talking about you can either just go forwards down the road or backwards down the road. So I guess that is helpful to a certain extent. Then it mentions they start by accelerating at a constant rate from 1 meters per second to 4 meters per second. Those are velocities, it's worth mentioning, although it says acceleration before that. The 1 meters per second and 4 meters per second are referring to velocities, and it tells us it does that in 5 seconds. So actually, we already have some information we can put on a velocity time graph. So let's start drawing that. So I've got some axes, and so we're going to do that. And unlike pure maths, where if you see axes like this, they're normally what we call a Cartesian graph, which basically means, posh way of saying, the axes labels are y and x. Instead, we're going to label the vertical axis v for velocity and the horizontal axis t for time. And when it comes to units, the normal default position in mechanics is to have velocity measured in meters per second, unless the question says otherwise, and then also time to be measured in seconds, because that's the standard unit for time in mechanics. So, if we're starting off with a velocity of 1 meters per second, it's almost like what was something we would call the y-intercept before. By now, I guess you could call it the v-intercept, if you will. And then it's going to go from 1 meters per second to 4 meters per second in 5 seconds. So by the time it reaches 5 seconds, it would have reached 4 meters per second. So therefore, we're effectively going from the coordinates 0, 1 to 5, 4. So I'm going to draw a line doing that. And that's because it says constant rate. Then we're maintaining this velocity. So that means we're staying at a velocity of 4 because that's the velocity we're currently at. And we're going to maintain that velocity for t seconds. So therefore, we're just going to go flat for a bit. So the y coordinate, or v coordinate I should say, is staying at 4. But if we're maintaining this for t seconds, watch out, because there would be a lot of people who would be very tempted to write t here. But that would be wrong. And the reason it would be wrong is because that implies this is happening at t seconds. But it's not. It's happening t seconds after we started going at 4 meters per second. And as we started going at 4 meters per second at 5 seconds, therefore if another t seconds has passed after 5 seconds, this time is t plus 5. So that's something to watch out for. Some students with this stuff just notate stuff wrong, so do make sure you're notating this stuff correctly. If you do want to point out that this interval was t seconds for this time period where it's maintaining that velocity of 4 meters per second, then what you can do is you can use arrows like this, showing that in between that time interval is t seconds. So that's how you do it, rather than marking actual values on the axis themselves, because values on the actual axis are saying that particular point on the graph is that value. Okay, and then what we're doing after that is we're then decelerating to rest. So that's the word I mentioned a few moments ago. Rest means velocity equals 0, so we're going to go back down to the t-axis because that's where v equals 0, and therefore we're just going to do that. So there you go. That is our velocity time graph drawn. Worth mentioning that all of these are straight lines. I haven't drawn it with a ruler. You could if you wanted to make the graph more neat, but I must admit the question said sketch, so that means generally the exam mark scheme is going to have a bit of leeway in there, just as long as it doesn't look too curvy, basically. You'll get away with it. Cool. But that's just drawing it, and I must admit, any drawing of velocity time graph questions are not worth that much because it's literally just drawing what you see in the words. However, things get more interesting when we actually start trying to use a velocity time graph to help us calculate stuff. And some of the things we need to be able to calculate using a velocity time graph are things such as, well, what happens if you calculate the gradient of one of the lines you've drawn on a velocity time graph? Well, that's just going to be effectively the v values divided by time values, and velocity divided by time is acceleration. So therefore, that's how you can find acceleration using a velocity time graph. On a side note, that also explains why in the previous example, when we had constant acceleration, I drew a straight line. Because ultimately, if we have constant acceleration, that implies that we've got constant gradient on a velocity time graph, and a graph with constant gradient means the gradient's not changing, and therefore it must be a straight line, because if we've got a graph with gradient that's changing, you've got a curve instead. So there you go. You could also decide to calculate area between a velocity time graph's line and the t-axis, and if you do that, you're finding the distance an object has travelled. I am being very careful to use the word distance there, not displacement, but that's something we'll talk about later in the video to make the distinction about what happens if you do want to find displacement. But yeah, for the moment, to make this sentence fully correct, yes, distance is what you're calculating if you find the area between a velocity time graph and the t-axis. In general, that's distance. And then one last tip I want to give you before we launch into example is sometimes some of the basic questions involving this stuff with straight lines do end up often involving trapezium shapes, and therefore, although you can work out areas of trapeziums by splitting them into triangles and rectangles, that takes way longer than just remembering from earlier education that areas of trapeziums have a formula, and the formula is half times the sum of the parallel sides multiplied by the height of the trapezium. So, with all that said, we can now launch into a second example, and we've been given a velocity time graph, and we are in part A just needing to work out the acceleration. So all we've got to do is work out the gradient of this part of the line that's going between t equals 0 and t equals 4. So the way you could do this is you almost could view this like coordinates. We're starting at 0, 0 effectively and going to 4, 9. So work out the gradient between those 2 points. So therefore, acceleration will equal the change in y, but it's the change in v instead. So 9 take away 0, divided by what would normally be the change in x, but now it's the change in t. So 4 take away 0, and therefore that's 9 over 4, but something worth mentioning for mechanics in case you haven't heard me mention it before, because we're now in applied maths, and applied maths is related to the real world, and the real world, people hate maths notation, they're scared of it, so therefore they prefer a decimal because it makes more sense to them. So generally we do that in mechanics. That's not like a set in stone rule, but it's just something we generally do. So writing 9 over 4 as a decimal, that would be 2.25, and then for units, acceleration units, it would be meters per second squared, ms to the minus 2, if time is in seconds and v is in meters per second. Cool, that's part A. It's really as easy as that. If it's a straight line, just work out the gradient of the straight line, and boom, you've got acceleration. And on to part B, where we're effectively just going to be using the other fact I mentioned before, the one about the fact that distance can be found using the area between the velocity time graph line and the t-axis. So that's what we're going to be doing. However, if you read the question, interestingly, it's going to require a bit more problem solving than that, because we've been given that the particle travels a total of 87 meters. So therefore, we actually already know what the distance is. And therefore, instead, what this question is requiring us to do is to find this mystery value of time, t, capital T. And therefore, it's one of those questions where you effectively know the answer, but therefore you're having to set up an equation to help you work backwards to find what the missing variable is. So therefore, to start this question off, we know we're going to need to find the distance ourselves using the graph and then set it equal to 87 meters to set up that equation. So we could start by finding the distance on the graph that's easy to work out, which is the area of this trapezium that I'm colouring in here. Because although you could work that out, as I said, using a rectangle and a triangle, it's quicker if you do it using the area of trapezium formula. So doing that, we know that it's going to be half times by the sum of the parallel sides, which would be the one at the bottom, which is just 7, because we're going from 0 to 7 on the t-axis, and then the one at the top, which would be a gap or interval, if you will, of 3, because we're going from 4 to 7, so 7 take away 4 is 3. And then you've got to multiply that by the height, and the height of this trapezium is 9. So there we go, you can work that out. That's just going to be 10 times 9 divided by 2, which is 45. Nice. Then the second bit is where it gets a bit more tricky, because we've got this unknown value of t, but that's still fine. All you've got to do is just still do a calculation to work out the area. It's just going to be in terms of algebra, in terms of t. Interestingly, this is another trapezium shape, so it makes sense to work it out as a trapezium, but it's worth noting it's trapezium turned on its side. So actually the height this time is this gap here, and that would be a gap of t take away 7. So therefore the area is half times by the sum of the parallel sides, which is now actually the lengths going up, confusingly. So that would be the shorter length of 5 and the longer length of 9. And then timesing that by the height, and we said our height is t minus 7. So therefore, 5 plus 9 is 14, times by half is 7. So we got 7 lots of t minus 7. So that means our total distance is 45 plus 7 lots of t minus 7. That's what we got the distance to be, but the question is telling us that it should be 87. So if you can set up this equation, because we know both of these things must be the same thing, they obviously currently don't look the same, so we need to solve the equation to then help us find what t is. I'm going to multiply out the brackets, so that will get us that. Then we can combine those two things. We can then add that thing on to get 91, and therefore divide both sides by 7, and you will get 13. So t equals 13. I don't actually need to put seconds there, because t was marked on the axis, so it's implied it's in seconds anyway. It's just a value of an algebra letter for this. But yeah, 13 seconds is what it's representing. There you go, we've done example 2. Just one more thing to mention though, as I hinted at earlier, displacement. What about if you want to find displacement using a velocity time graph? Well, I should point out the distinction of what I said earlier. I did point out that distance equals total area between the velocity time graph and the t-axis. And that's interesting in examples like this, because there's actually two different areas that are going on there. You've got this first triangle, which you can work out as an area between that line and the t-axis. So that would be, of course, a triangle, so half times base, which is 8, times by height, which is 6. And if you work that out, of course, that's just going to be 24. But then, also, it would be this area as well added on. So therefore, the area of this triangle, it's another triangle, so again, do the same sort of calculation. Half times the base, this time the base is 3, because we're going from 8 to 11, times by the height, and the height has a length of 5. It's going down to minus 5, but that's just to tell us, in terms of almost coordinates on an axis, but there's a length of 5. So therefore the area is 15 over 2, or 7.5, whatever you prefer. And therefore the total distance is going to be 24 plus 15 over 2, and so therefore that is 31.5. Nice, so 31.5 meters. and that is the distance. So if you want to find distance, it's always the total area between the line and the t-axis, regardless of whether the graph is above the t-axis or below the t-axis. However, if you want to use a velocity time graph to find displacement, well, it all depends on whether your line is above the t-axis or not. If your line, like in some of our previous examples, were fully above the t-axis, then actually, if you calculate the area between the graph and the t-axis, you are also finding displacement, because we only went in one direction, so therefore displacement and distance are equivalent in that case. But if you got a situation like this where the velocity is above the t-axis for a part of the graph and then below, that's important because it means we're changing direction. So that means the displacement and distance aren't the same, and instead displacement is going to equal the area between the velocity time graph and the t-axis that's above the t-axis, and therefore for us before that was 24 that we calculated already, minus the area that's between the velocity time graph and the t-axis that's below the t-axis. So for us, we had this second area that was below the t-axis, and therefore that's a number we'd have to subtract from 24 if we wanted to find the displacement. So therefore, for us, that would end up calculating as 16.5 meters. So the displacement and distance are calculated in slightly different ways in these sort of scenarios. Another way of looking at it to explain why we're taking away the area that's below the t-axis is partly because, going back to what I said when we were calculating the height of that triangle that's below the t-axis, we said the height has got a length of 5, but if you're looking at the coordinates, it's kind of like it's got a length of -5, if you will. So that's kind of what's going on. You could calculate that second triangle as being half times 3 times -5, and that explains why we're treating it as a negative number and taking it away. So just to be aware of that, it does also, by the way, have links to the integration chapter, if that's something you've covered yet, to explain how things being above and below an axis are calculated in different ways when it comes to area. Okay, hopefully you found this information useful. That's how you deal with velocity time graphs. That's how you calculate things involving them. Sometimes you need to calculate areas in terms of algebra and set up equations. Some students freak out about that, but just do the same steps, but just with algebra. And you're a Maths A-level student, so algebra, that's just our usual stuff. It's just every day. So there you go. See you in a future video. Goodbye.